Have you ever wondered why, despite all our powerful computers and massive datasets, AI still struggles to adapt when the real world changes? We often assume the answer lies in building bigger models or feeding them more data. But what if the secret to true robustness isn't about adding more complexity, but rather about choosing the right mathematical rules in the first place? Welcome to a journey through the latest breakthroughs that are reshaping how we build artificial intelligence. Today, we are diving into a collection of new research that challenges our conventional wisdom. We will explore why the mathematical foundations of our models matter more than their structural complexity, how simple geometric shapes are revolutionizing video production, and why compressing information is the key to unlocking creativity in images and music. Stay until the end because these findings offer a surprising roadmap for engineers and creators alike, proving that sometimes less really is more. For years, the tech industry has operated under a specific assumption. To make AI better, we need to make it bigger. We pour resources into training massive neural networks on endless amounts of data, believing that sheer scale will solve issues like domain shifts. Those moments when an AI trained on one type of data fails to perform when faced with something slightly different. This approach has led to incredibly complex systems that are often brittle, struggling to adapt when deployed in dynamic, real-world environments. Furthermore, in fields like video production and creative generation, the reliance on dense, frame-by-frame processing or high-resolution pixel manipulation has created bottlenecks, making content creation labor-intensive and computationally expensive. The core problem is a misallocation of focus. We have been obsessing over the representation of data while neglecting the fundamental statistical rules that govern how that data is interpreted. However, a wave of new research is flipping this narrative on its head. A systematic study on anomaly detection has revealed a startling truth. The choice of the scoring backend, the mathematical engine driving the model, is far more critical than the method used to aggregate features. Researchers found that shifting the scoring backend, such moving from one statistical distribution to another like Mahalanobis, improved robustness against domain shifts by a massive 13.8%. In contrast, optimizing feature pooling strategies only moved the needle by 3.2%. This suggests that the rules we use to judge data are the true drivers of success, overshadowing the complexity of the model architecture itself. This principle of structural simplification extends beyond sound detection into the visual world as well. A new framework called loose control video is transforming how we manage complex scenes by using sparse, oriented three-dimensional boxes as proxies, instead of dense, frame-by-frame guidance. By decoupling semantic structure from heavy data loads, this approach has achieved a 1.2 to 3-fold improvement in trajectory error and doubled the consistency of rigid motion. It allows creators to refine local elements without disrupting the global context, proving that geometric priors can simplify the most chaotic visual environments. The momentum continues in the realms of image and music generation, where efficiency is being unlocked through compression. New frameworks are now leveraging compressed latent spaces to drive diffusion models, shifting the computational burden from high-dimensional pixel spaces to lower-dimensional representations. This shift not only reduces complexity, but also bridges the gap between discrete text and continuous audio. By integrating textual inversion into the diffusion sampling loop, researchers have created a unified pipeline that maps semantic text inputs directly to auditory outputs. This moves us beyond traditional sequence-to-sequence models, allowing AI to handle the stochastic nature of cross-modal tasks with unprecedented robustness. So, what does this convergence of findings mean for the future of AI and humanity? It signals a pivotal maturation of the field. We are moving away from an arms race of model capacity and toward a deeper respect for mathematical foundations and geometric intuition. For engineers, this offers a clearer, more efficient path to deploying robust systems that do not require constant retraining when the world changes. For creatives, it promises tools that reduce labor intensity and unlock new scales of content generation. The message is clear. By prioritizing the statistical calibrations and geometric priors that underpin our data, we can build AI that is not just powerful, but truly adaptable. As we wrap up, remember that the next frontier of innovation isn't about building bigger machines, but about understanding the elegant rules that govern them. The research we explored today proves that optimizing our mathematical assumptions yields greater efficiency than simply expanding model complexity. If you found these insights as fascinating as I did, please like this video, subscribe to our channel, and comment your thoughts on whether you think mathematical simplicity will dominate the future of AI. Stay tuned for our next episode, where we will explore how these compressed latent spaces are being applied to solve real-world climate challenges.